In this section and the next one, we look at relativistic dynamics. And dynamics, you will recall, is the branch of mechanics that deals with things like momentum and energy. Now, in classical physics, momentum of an object of mass m, which is moving at a velocity v, is given by m times v. It's just the product of the mass and the velocity. However, this equation, this definition of momentum does not work at relativistic speeds. For example, it creates problems such as it allows for infinite amount of energy. It allows for speed of an object to exceed the speed of light and so forth. Now, in classical, so obviously this equation needs to be modified. In classical physics, we saw that momentum is one of those quantities that is conserved as long as there are no external forces present. And that's a helpful tool to analyze different situations like collisions and so forth. So conservation of momentum is a fundamental law of physics which helps us analyze different phenomena, collisions, impact of a moving object on a wall, etc. When you come to relativistic speeds, the momentum is also conserved. Relativistic momentum is also conserved and is again a helpful tool in studying certain types of phenomena in modern physics. Most of what is known about fundamental particles is learned from particle accelerators. These are giant machines which accelerate beams of particles, and in many situations, these beams of particles coming from opposite directions collide with each other at relativistic speeds. And then physicists see what happens. In many cases, these tiny particles smash and give rise to other particles, and other such events happen. So what happens in a particle accelerator, what happens when beams of particles collide with each other, gives us important insight into the nature of particles, nature of atomic physics. At relativistic speeds, the momentum is defined as P equals gamma mu. So instead of just mu, there's a factor of gamma now. Instead of just mass times velocity, this is mass times velocity times gamma. So m is the rest mass of the object. It's the mass of the object when it's at rest. It's basically the mass that we have been talking about in classical physics. U will be used to represent velocity of the particle, of the object relative to an observer. And then gamma, you will recall, is 1 over square root of 1 minus u square over c square. You might be wondering why we are using u instead of v. V is typically used for relative velocity of two observers, or relative velocity between two frames of reference. Whereas if you're talking about relative velocity of an object relative to one observer, then it's common to use the letter u. Okay, so relativistic momentum is gamma mu, and then which makes, if you plug in the expression for gamma, this becomes mu over square root of 1 minus u square over c square. So that's the relativistic momentum. Now, as you've seen in the past too, that if objects are moving at non-relativistic speeds slower than much slower than the speed of light, then results of relativistic physics basically go back to what classical physics says. So in this case also, if u is much less than c, then gamma becomes equal to 1, because this second term in the radical becomes 0. And that gives us back the equation that P equals simply mu, the classical equation for momentum. On the other extreme, if as the speed of the particle approaches the speed of light, as u approaches c, P approaches infinity. And again, you can see in this equation, if u is equal to c, then the second term in the radical is 0, and then 1 minus 1 is 0. So and when you divide something by 0, you're basically making it infinitely large. And this is another indication that objects with non-zero mass cannot reach C. You can't have infinite momentum, and so no particle can move with the speed of light. Let me pull up the book here. Let's see. So this is the graph of momentum as a function of u, as a function of speed. Now you'll recognize this function, momentum as a function of u. It's a rational function and will have a vertical asymptote whenever the function is undefined. So in this case, as I noted earlier, the function is undefined, or it approaches infinity when u approaches c. So that's why the vertical asymptote is at this location, where the speed is equal to 1c, or it's equal to the speed of light. And then as you increase the speed, it basically grows exponentially and then approaches 1c here. All right, let's look at problem number 40. Problem 40 says, find the velocity of a proton that has a momentum of 4.48 times 10 to the negative 19 kilograms meters per second. So that you'll recall is the SI unit for momentum, kilograms meters per second. So in this case, we are given the momentum and we have to find u. We are given p and we have to find u. One other thing you'll need to know is the mass of a proton, which you can look up, and is equal to 1.673 times 10 to the negative 27 kilograms. So basically, you need to solve this equation for momentum. You need to solve that equation for u. Notice that there's a u in the numerator, but also in the radical in the denominator. So it takes a bit of a math. So you can start by multiplying both sides by square root of 1 minus u squared over c squared, and then square both sides of the equation, which gives you p squared, and then the square root disappears, and on the right you have m squared u squared. And then you distribute the p squared, so p squared minus u squared p squared over c squared equals m squared u squared. And then in order to solve for u, you first bring all the terms that have u in them to the left. Everything else goes to the right. And once you do that, you will then factor out a u square, and that leaves you with u squared times m squared plus p squared over c squared equals p squared. And divide both sides by this parentheses here. So u squared equals p squared over n squared plus p squared over c squared. And then you multiply top and bottom by c squared to simplify this a little bit. So you end up with p squared c squared in the numerator. And when you multiply the denominator by c squared, in the first term, you just get m squared c squared. In the second term, the c squared cancels the c squared in the denominator. So that's the end result here. And then you take the square root to solve for u, and that gives you this equation. U equals pc over square root of p squared plus m squared c squared. And then you plug in the numbers and you get the answer that it's 2 times 10⁸ meters per second. That's how fast the proton would have to go in order to have this momentum. That brings us to the second part of dynamics in which we look at energy. Like conservation of momentum, conservation of energy, as you know, is an extremely important part of the study of physics. It comes in handy. It's helpful for many different things. So conservation of energy too is fundamental property in classical physics, and the same in relativistic physics. However, what we mean by energy has now to be modified. It needs to be expanded in order to maintain the conservation of energy. So, and that's what we will do now. Now, energy is conserved in relativistic physics if it is defined as this. So energy of an object, of a particle, is equal to gamma mc squared. Again, the symbols are familiar to us by now. Gamma is 1 over square root of 1 minus v squared over c squared. M is the mass, c is the speed of light. Now, this is the total energy. You'll remember from first semester that we studied different forms of energy. The E here includes both the potential and kinetic energies. And this is called the total energy. Now, if an object is stationary at v equals 0, E is equal to E naught. We call that the rest energy. It's the energy of an object at rest. From this equation, if v is 0, this second term in the radical becomes 0, So E is just equal to mc squared over square root of 1, which is just 1. So the rest energy of an object of mass m is E equals, or E naught equals mc squared. And that's the famous equation that came from Einstein and has made into popular culture, popular language, and popular imagination. So this is called the rest energy. It's the total energy of an object at rest. Now, one outcome of this equation is that energy and mass now become interchangeable. If you have an object of mass m, which is at rest, then even though it's not moving, it still has a certain amount of energy given by the mass times the square of the speed of light. So mass can be converted into energy, and energy can be converted into mass in accordance with this equation. So mass and energy are interchangeable. In classical physics, we talked about conservation of energy, whereas now we want to expand that and talk about conservation of mass energy, not just energy, but mass energy. So energy and mass can be converted into each other, but if you take the total of mass and energy, then that total remains constant, it remains conserved. One example of how mass can be converted into energy and vice versa comes from the field of nuclear energy. So nuclear energy is created through reactions that take place inside the nucleus of an atom, nuclear reactions. And in nuclear reactions, some of the nuclear mass, some of the mass of the particles in the nucleus is converted to energy, and that is what nuclear energy is. So when you create nuclear energy, there's a reduction in mass of the particles involved, and that reduction in mass shows up as energy. So you can think of mass as being as a form of energy also. When energy is stored in an object at rest, for example, elastic or gravitational potential energy, remember, in order to have gravitational potential energy, the object doesn't have to be moving, it just needs to be at a certain height. Similarly, elastic potential energy is the energy associated with, for example, a stretched spring. So in both cases, you don't need motion. It's an object at rest that has these energies. So when there is stored energy in an object, either gravitational potential or elastic potential, that energy shows up as mass. So you can think of it as its mass having increased. The mass increases if an object has elastic potential energy or gravitational potential energy. And by how much does this mass increase? That's in accordance with this equation. If it has a potential energy of E naught, then the increase in mass is given by this equation. Now, the fact that speed of light is so huge, the mass equivalent to elastic potential energy or gravitational potential energy will be very small because m is E naught over c squared, and c squared is huge. So even though there is some amount of increase in mass, if an object has potential energy, it's too small. That increase is too small to observe in everyday life. But this is how you can calculate uh, the increase in mass. It's the potential energy divided by c squared. All right, let's look at problem number 46. All right, problem 46. The Big Bang that began the universe is estimated to have released 10 raised to 68 joules of energy. How many stars could half this energy create, assuming the average star's mass is 4 times 10 raised to 30 kilograms? So you're given the total energy released at the time of Big Bang, and then you have to see how many stars can you create out of that energy. So we're only going to use half of that energy, as the problem says, which means the energy available to us for creating stars is 10 raised to 68 divided by 2. The mass of each star is 4 times 10 raised to 30 kilograms. So the energy of each star, energy, remember, is mc squared. So the energy of each star would be 4 times 10 raised to 30 times the square of the speed of light. Speed of light being 3 times 10 raised to 8. When you square it, you get 9 times 10 raised to 16. So when you multiply that by 4 times 10 raised to 30, the energy of each star comes out to 36 times 10 raised to 46 joules. So how many stars can we create out of the available energy? That's the available energy divided by energy corresponding to each star, and that gives us this number. So even if you used half of the energy available to create stars, you're able to create 1.389 times 10 raised to 20 stars. Okay, if you if you focus on kinetic energy, classically we know kinetic energy of an object of mass m moving at a velocity v is 1/2 mv squared. Relativistic kinetic energy is derived from work energy theorem, which you will recall from first semester. Work energy theorem basically says that if you do a certain amount of work on an object, its energy changes by that amount, by the amount of work that you do. So if you do positive work of 5 joules, the energy would increase by 5 joules. If you do a negative work of 5 joules, the energy would decrease by 5 joules. So that's the essence of work energy theorem. So net work done is equal to kinetic energy for an object that's starting from rest. So the object is at rest, you do a certain amount of work on it, say 10 joules, then at the end of it, that object will not be at rest anymore, it will be moving with a kinetic energy of 10 joules. So at rest, we defined the total energy to be the rest energy, which is mc squared. When you do work on it, this energy increases, and the total energy becomes gamma mc squared. So the net work which is done is the final energy minus the initial energy, or gamma mc squared minus mc squared. If you factor out mc squared, you get gamma minus 1 times mc squared. So that should be the equation for the relativistic kinetic energy. Relativistic kinetic energy is gamma minus 1 times mc squared. If the object is at rest, then gamma is 1, because v would be 0. And if gamma is 1, this equation basically gives us that the kinetic energy is 0, which is what you would expect. You know, if for an object at rest, we expect the kinetic energy to be 0. Again, in order to bring back what we've been saying, that if the object is moving very slowly, then these equations should convert back to classical results of classical physics, and that's true for kinetic energy as well. Uh, so if the velocity of the object is much smaller than speed of light, let's see what happens to kinetic energy. In order to figure out the answer, we have to use something called the binomial expansion, which some of you might have seen in mathematics or calculus. Uh, Basically, binomial expansion is a way of writing expressions, algebraic expressions involving powers as sums and differences. Binomial expansion for square root of 1 plus x squared is given by this. So 1 plus x squared raised to 1/2 is 1 plus x squared over 2 minus x to the 4th over 8 plus x to the 6th over 16th, and so on to infinity. So it's an infinite series. So if we use this binomial expansion for gamma, which is 1 over square root of 1 minus v squared over c squared, or 1 minus v squared over c squared raised to 1/2, negative 1/2, sorry, then that gamma becomes 1 plus v squared over 2 c squared, and then v to the 4th over c to the 4th, etc. However, if v is much less than c, then we can ignore the higher power terms. If v is much less than c, then v to the 4th is going to be much, much, much less than c to the 4th. So we can ignore all of the later terms here, which means kinetic energy is 1 plus v squared over 2c squared minus 1 times mc squared. If gamma is 1 plus v squared over 2c squared, then if you go back to the equation for kinetic energy, this one, you basically get that. And then when you distribute the mc squared, you can see that the equation for kinetic energy is 1/2 mv squared, exactly what we had in classical physics. You can also see what happens as the speed of a particle approaches speed of light. Again, gamma approaches infinity, so kinetic energy approaches infinity as well. So that means it would take infinite amount of work to bring an object speed to speed of light, to c, and which is also not possible. Okay, so if you make a graph of kinetic energy as a function of speed, in accordance with the relativistic equation and the classical equation, this is what you get. Classically, kinetic energy is 1/2 mv squared. So you can increase the speed to whatever you want, and the value of kinetic energy keeps growing as a square function, as a quadratic function. So that's this thing, and that's the graph in the green. However, a relativistic kinetic energy has a factor of square root of 1 minus v squared over c squared in the denominator, and that puts a limit on how much the speed can increase before kinetic energy becomes infinitely large, which is not possible. So we basically get a vertical asymptote at v equals c. And as you can see, the red curve, which is the relativistic kinetic energy, cannot even touch this because kinetic energy is approaching infinity as the velocity approaches c. So once again, it basically says that the speed of an object cannot reach the speed of light. There's an alternate unit for energy that's used in particle physics, atomic physics, nuclear physics, etc. And that's called the electron volt. We defined electron volt in second semester when we're talking about electrical energy as well. But this is how the conversion factor is. 1 electron volt is 1.6 times 10 to the negative 19 joules. You will recognize 1.6 times 10 to the negative 19 as the charge of an electron. So 1 electron volt is basically that energy which an electron will have if you accelerate across a potential difference of 1 volt. For higher energy particles, it's convenient to use MeV, mega electron volts. So 1 MeV is 1.6 times 10 to the negative 13 joules, basically off by a million. All right, let's look at problem number 57. Okay, so problem 57 reads, what is the kinetic energy in MeV of a pi meson, which is one of the many subatomic particles? Kinetic energy in MeV of a pi meson that lives 1.4 times 10 to the negative 16 seconds as measured in the lab, and 0.84 times 10 to the negative 16 seconds when at rest relative to an observer, given that its rest energy is 135 MeVs. So we're given times measured from two different frames of reference. So we'll have to use time dilation equations to figure out what gamma is. Okay, so this is what we have. You have to figure out kinetic energy. So you have to be able to distinguish which one is delta t, which one is delta t naught. Delta t naught, the proper time timer, is a time measured by an observer at rest with respect to the event. So delta t naught would be 0.84 times 10 to the negative 16 seconds, which is what's measured by an observer at rest relative to the meson. And therefore delta t is 1.4 times 10 to the negative 16 seconds. It's measured in lab, and presumably the pi meson is moving in lab. So this is the time measured when the particle is in motion with respect to the observer. Okay. Now the rest energy of meson is 135 MeVs, and rest energy we know is mc square. And you have to figure out the kinetic energy. Kinetic energy is gamma minus 1 mc square. So you plug in 135 for mc square. Keeping in mind this is in mega electron volts, MeVs. From this, you will need to know what gamma is before you can find Ke. And using the equation for time dilation, gamma is delta t over delta t naught. You'll recall the equation for time dilation is delta t is gamma times delta t naught. So that's where this comes from. plug that into the kinetic energy equation, and you get this, which comes out to 90 MeVs. So the kinetic energy of such a pi meson is 90 mega electron volts. Now, after some complicated algebra, it can be shown that the square of the total energy is equal to Pc squared plus Mc squared squared. And anyway, I mean, this is not really relevant, but in kinetic energy, in classical physics, the classical kinetic energy is momentum square over 2m, p square over 2m. Since momentum is mv, you square it, divided by 2m, you get 1/2 mv squared. So kinetic energy is p squared over 2m is the classical equation, which tells us how kinetic energy and momentum are related. And in relativistic physics, energy and momentum are related by this equation. E squared equals pc squared plus mc squared squared. If the object is at rest, P is 0, momentum is 0, and that brings us back to rest energy. If the first term is 0 here, and then you take the square root of both sides, you get E naught equals mc squared. And then again, at sufficiently high velocities, mc squared would be much bigger than pc squared if you approach the speed of light. I'm sorry, much smaller than that if you approach the speed of light. So this mc squared, which is the square of the rest energy, can be ignored at high energies. So the second term in this equation can be ignored if the speed of the particle is close to the speed of light. So that brings us to E squared equals Pc. E squared equals Pc. Now, one thing that's kind of a surprising and unexpected and not seen in classical physics is that now massless particles can also be seen as having momentum. If E is equal to Pc, and if you solve this equation for P, then P becomes E over C. So even if an object or particle does not have any mass, all it has is some amount of energy, you can still associate a momentum with it. Momentum is energy divided by speed of light. And an example of a particle which does not have a mass is a photon, which is a particle associated with light. And we'll talk about photons more in a later chapter. So that brings us to the end of this chapter. It brings us to the end of our discussion of special relativity.